Today, we're finishing up separation of variables for Laplace's equation. So last time, we talked about multiple things. We talked about the maximum principle, and we started on this problem of Laplace's equation on a disk, right? So the Laplacian of u equals 0, u equals f on the boundary of a disk. And the PD is defined on the interior, which is a two-dimensional disk, okay? And we essentially found that by assuming that, well, first of all, we assumed or changed to polar coordinates, right? And then we assume that we have solutions of the form capital R of R, H of phi, okay? And then we got a nice Sturm-Liouville problem, and our series solution, I'll go through all the steps again. Series solution is of the form u of R phi is equal to A0 over 2 plus the sum from n equals 1 up to infinity, r to the n, an cosine of n phi, plus bn sine of n phi, close parentheses there. And given our boundary condition, and we had written this as UA of phi is equal to f of phi, right? Then we can obtain the following, right? So we have an bn as a vector is equal to 1 over an pi integral from 0 to 2 pi f of phi, cosine of n phi, sine of n phi, d phi, okay? All right, so, I mean, not a lot new that we worked through here. However, we did have to deal with this boundedness condition at r goes to 0. And whenever you're solving problems on disks or balls, you'll usually end up with that because you can potentially have singularities, especially if you have, you know, Laplacians involved, either in the, you could have this with a wave equation on the disk, you could have a heat equation on the disk, right? You're going to run into similar things, right? So what we're going to do is we're now going to translate this solution into something that reveals a little bit more information about the kind of kernel that we're integrating against f. And so our solution now, if we plug in actually what these coefficients are, okay, we can write it in the following way, okay? If I pull out the integral and I change the dummy variable inside of these coefficients to phi prime, then I have f of phi prime times now everything that was in here, right? But now I've substituted in what a, n, and bn are, okay? So we're gonna sub in a, n, and bn. And we get 1 plus 2, the sum from n equals 1 up to infinity, r over a now to the n, right? Because I have an r to the n and I have an a to the n here. cosine of n phi, that's this cosine of n phi, but then I have a cosine of n phi prime, which is this one, right? That I'm changing that dummy variable there. Sine of n phi, sine of n phi prime. And that's all I have there, although I've smushed myself a little bit there, okay? But we can close all these parentheses and we're integrating with respect to d phi prime, okay? Now, we can collapse this a bit, okay? And I'm going to make the following claim that u of r phi is equal to 1 over 2 pi integral from 0 to 2 pi f of phi prime 1 plus 2, that sum again, right? R over A to the n. And I'm just going to use a trig identity now that tells me that cosine of something times cosine of something else plus sine of that first thing times sine of something else is cosine of the first thing minus the second thing, okay? So cosine of x plus times cosine of y plus sine of x times sine of y is equal to cosine of x minus y, okay? So this thing here now in total, this is what's called the Dirichlet kernel, okay? And you can see here now what we have a convolution, okay, of the Dirichlet kernel against our boundary condition, okay? So you should be reminiscing maybe a little bit about what happened with the heat equation, right? What happened with the heat equation is you take some initial condition, you convolve a fundamental solution against it, right? And that sort of, smooths out the initial condition over time. Here, we're taking a boundary condition and we're convolving a kernel against it, and it's sort of smearing the boundary condition to the interior of the disk. So it's telling you about how the boundary condition propagates to the interior of the disk when you're satisfying the Laplacian, when you have a harmonic function, okay? So we can show essentially that 1 plus this thing, my Dirichlet kernel, right? 1 plus 2 times n from 1 to infinity, a cosine of n phi minus phi prime. We can actually show that this is equal to a squared minus r squared divided by a squared minus 2ar cosine of phi minus phi prime plus r squared, okay? So we can collapse that infinite sum using some geometric series identities and such down to just a standalone function there, okay? And so how do we do that? So we write 1 plus 2, and I'm just gonna call r over a, I'm gonna call that capital R, right? So this will just be r over a here. And I'm just gonna write this as cosine and phi. So my phi will just be, sorry, theta. My theta will be phi minus phi prime, okay? So we can use complex exponentials, right? R to the n, e to the in theta, e to the minus in theta plus 1, okay? And if you know geometric series, now you probably see where we're going with this, right? We can combine those things and then use the geometric series identity, right? So I can write this now as, I'll write it down here, the sum from n equals 1 up to infinity, r e to the I theta, excuse me, to the n plus r e to the minus I theta to the n plus 1, okay? And using geometric series, okay, we just have that those sums are 1 over 1 minus r e to the I theta plus 1 over 1 minus r e to the minus I theta. And then I get a, right? I get a minus 1. Is that right?
Yeah, I think the sums start at 1 instead of 0.
Oh, yeah. That's right. Yeah. Okay. Yeah, that's right. So we get a minus 1. Okay. Thanks. All right. So we can do a couple steps. It's just a bit of algebra, and we can show that we have 2 minus 2r cosine theta divided by 1 minus 2r cosine theta plus r squared minus 1. Okay. And combining those, finally, we get 1 minus r squared over 1 minus 2r cosine theta plus r squared, okay? And so we've collapsed now our Dirichlet kernel to just a function rather than an infinite series. Great, okay? And the result is what's called Poisson's formula, okay? And Poisson's formula, again, just says that our solution is equal to 1 over 2 pi integral from 0 to 2 pi a squared minus r squared divided by a squared minus 2ar cosine of phi minus phi prime plus r squared, okay? All of this times f of phi prime d phi prime, okay? All right, and so we call this, right, because this is Poisson's formula, we call this the Poisson kernel sometimes, okay? So the Poisson kernel, and it's really like u of r phi is equal to p of r minus a, some argument convolved with f as a function of phi, okay? Where our Poisson kernel, right, is going to be p of r over a psi, let's call it that, 1 over 2 pi, 1 minus r over a squared divided by 1 minus 2 r over a cosine psi plus r over a squared. So you see those r over a factors just show up everywhere, right? And so the Poisson kernel has nice properties. It sort of behaves like this kind of fundamental solution because it's singular at r equals a, okay? And it's, in principle, it's an example of what's called a Green's function, which we'll unpack a bit more in a couple weeks, okay? So I can wrap up by just stating a few properties of the Poisson kernel, okay? And then, yeah, actually, we will start on some background on Green's functions today, okay? Questions about this so far?
So there's geometric intuition to be had here, right? Because the denominator is law of cosines. So, and I guess drawing on previous stuff I've seen in electromagnetism, I imagine the kernel to be something like, you know, a vector over that vector projected onto another axis, or
right,
something like that.
Yeah. So that's a good, yeah. So we'll have a good geometric interpretation. Yeah, I'm about to write that out, but yeah, your intuition is right. Yeah, yeah, a good call on that. Okay, so I'll just jump into the properties then, and